Welcome back. We're going to move into video 2 for Unit 4 as we look at means to represent with the various numbers of models the notion of multiplying. So let's go right back to this PowerPoint and get back into it, shall we? All right, let's go. Boom. All right, I got to get back and share. Ready? There it is. All right, from the current slide. There we go. If you remember from our last unit, we looked at properties as they related to addition, and then we looked at them in terms of subtraction. And we found that while addition did tend to be commutative and associative, subtraction came up a little bit short and wanting on those. So we'll look at those same properties as they relate to multiplication for whole numbers. First of all, we're just going to flat out come out and say that the set of whole numbers is closed with respect to multiplication. And that simply means if you grab any two whole numbers, whether they are unique or whether they are the same, and multiply them together, you will in fact get an answer that is a whole number. So we do have closure as it applies to the operation multiplication. Multiplication is commutative, and that simply means order doesn't matter. 2 times 5 is going to get you the same answer as 5 times 2. So much like addition, order doesn't matter on this particular operation. That was contrasted with subtraction, wherein order matters a lot. Associative, changing groupings again, whether you take A times B and then multiply that result times C, you will get the exact same response if you would have multiplied the second two numbers first, B and C in this case, and then multiplied that result by A. We found that there was this unique special number relative to addition, and it was 0. In this case, the unique special number relative to multiplication is 1. So A times 1 gets you the same answer as 1 times A, and they both get you the answer A. So we will say that 1 is the identity element as it relates to multiplication for whole numbers. If you take any whole number and multiply by 0, you get 0. Okay. These next slides hopefully will show you why some of these properties work. So on the left side, you see 3 times 5, and you see it as 3 rows and 5 columns. And if we change those dimensions and showed 5 rows and 3 columns, holy smoke, we are showing the exact same response. So we've just showcased 3 times 5 having the same output as 5 times 3. This one I think is harder to look at. The little figure over there, A, you're looking at some 5 by 4s. And you actually, if you count them on the stack, you have 3 of those 5 by 4s. If you contrast that with the guy in the middle, there it looks like you have 3 by 5s, and it looks like you have 4 in that stack. And if you look at the whole thing on the right-hand side, it's a whole bunch of 5 by 4s and 3 high. And so it's a visual approach for you and I to illustrate what it means to be associative as it applies to multiplication. You may remember the distributive property, and on the model on the left, you and I are seeing 5 rows, and then you see 3 columns, and then immediately attached to it, another 4 columns. And the kicker here is that we kind of tore that apart. We looked at 5 times 3, and then looked at 5 times 4, and put those two areas together. We would, in fact, have the given area that you see on the left-hand side. So that's a visual approach for your distributive property. For those of you who remember the distributive property way back from your fond memories of algebra, when you take A times the quantity B plus C, it's A times B, and then also A times C. Mistakenly, oftentimes people mess up the back part. They forget to take A times C. Should point out that distributive property alpha also works relative to subtraction inside that set of parentheses. So this would just get you A times B minus A times C. All right, when you first learned to factor, way back in Algebra 1 or possibly pre-algebra, the first kind of factoring you did was greatest common factor factoring. So in this case, if you look at the expression AB plus AC, some teachers said, oh, you know what? Each of those expressions has a factor of A. We can factor that out. So what we saw as greatest common factor factoring was really distributive property kind of going the other direction. And that's how we learned to factor first. We factored out that common factor A, and we were left with 2 factors, namely one would be A, and the other would be the quantity B plus C. Okay, so we're going to try to do an area model. So what we're going to see here now is we're going to see a rectangle show up. And one of the dimensions of the rectangle is going to have a distance of x plus y. The other one is going to have a distance of z plus w. So there you see across the top, the distance from left to right is z plus w. The distance from top to bottom, the other dimension, if you will, is x plus y. And you can see that we have, in fact, 4 little rectangular shapes that each has an area. So the top left rectangle has dimensions x by z, that's xz if you multiply. The top right has dimensions x by y, that's xy. The bottom left has dimensions y by z, yz. And the last one on the bottom right has dimensions y by w, and that would be yw. And what you've just modeled by means of this rectangular area kind of approach is exactly what you and I once upon a time called firsts, outsides, insides, and lasts. Some of you remember that as being called FOIL, right? So that's a model for us in terms of multiplication. Can we do it again? Sure, why not? All right, what happened on that? Well, we took the parenthesis set x plus y, multiplied it by z, and then multiplied it by w. And we're going to do a distributive, in which case the first guy gets z times both x and y. Second guy gets w times both x and y. And we've just said, hey, look how much fun we're having. What do we do there? Looks like we just changed the order. We put together the x guys to the front. We took the y guys to the back. I like this model approach. Technically, you could use any 2 numbers that would add to 17, and you could use any 2 numbers that would add to 22. I think it's important probably to showcase this most with 17 as 10 plus 7, so you get place values involved. And 22 then would be 20 plus 2. So you'll see on the screen, I got a lovely little rectangle. Looks like we'll probably take the top distance across and make that 22. So I'm going to show you that as 20 plus 2. Oh, that's pretty clever. And then I'll take the other dimension, which will be 17, and we'll show you that as 10 plus 7. So there's the 17, 10 plus 7. There's the 22, 20 plus 2. And much like before, you see 4 individual rectangles, and we could find those areas. Top left would be 10 by 20, 200. Top right would be 10 by 2, 20. Bottom left would be 7 by 20, 140. Bottom right is 7 by 2. If we added those areas together, we will in fact find the answer to the multiplication problem, 17 times 22. I do believe that's 374. So I like the approach a lot. The idea of using a rectangular model to showcase what happens when we multiply 2 two-digit numbers together. Again, there's nothing magic about the 17 being 10 and 7. Could have gotten the same answer if we would have used 15 and 2 for 17, if we would have used 10 and 12 for 22. I like the fact that we gave some special idea to place value. So I like the 20 and I like the 10. That, my friends, is a wrap on video 2 for Unit 4. I'll be back soon with video 3. See you then.